Let's kick things off with a massive question. Will humanity ever be able to leave the Milky Way galaxy? I mean, just imagine it for a second. One day, we're not just hopping over to Mars, but we're literally packing our bags and crossing the entire galaxy.
I know, it sounds straight out of a science fiction movie. But the real scientific question is, can we actually cross that unimaginable edge of the Milky Way? And if we can, how many millions of years is that going to take us? This is exactly where the mysterious story of wormholes and cosmic distances begins.
Okay, so to really grasp the scale of this challenge, we first need to understand just how gigantic our home galaxy is. And to do that, we look at the universe's absolute speed limit, the speed of light. Light travels at a mind-bending 300,000 kilometers per second. And remember, a light year isn't a measure of time, it's a measure of distance. It's how far light travels in one entire year. Now, our galaxy is definitely not a small neighborhood. It is spread out over roughly 100,000 light years. So even if you were cruising at that absolute maximum speed of light, it would still take you 100,000 years just to get from one side of the Milky Way to the other. And here's the reality check. We humans, we haven't built anything that can travel anywhere near the speed of light. Take our fastest spacecraft, Voyager 1. It's out there cruising at a mere 17 kilometers per second. Compared to light, that's practically standing still. So, if we ever try to reach another star system, distance itself is our biggest enemy. Leaving the entire galaxy, that's on a whole other level of impossible right now. But that brings up a really fascinating question. Do we actually have to travel the normal way? Is there some kind of cosmic loophole? Let's do a quick thought experiment. Imagine you have a flat piece of paper. You're on one corner and your destination is on the opposite corner. If the paper stays flat, you have to trace a long, tedious line all the way across. But what if you fold the paper, bringing those two corners right next to each other? Suddenly, that massive distance is practically zero. This is the core concept of spacetime, described by Einstein's general theory of relativity, which shows us that mass and energy can literally bend space and time. And this brings us to the famous wormhole. You can think of a wormhole exactly like folding that piece of paper. It's a hypothetical shortcut through the very fabric of space and time. So, in theory, instead of spending billions of years crossing normal space, a funnel-shaped tunnel could instantly connect two incredibly distant locations. Now, I know this sounds like pure Hollywood magic, but it's actually grounded in real physics. Building on Einstein's work, 3 scientists, Morris, Thorne, and Yurtsever, published a groundbreaking paper back in 1988. They brought the theoretical concept of traversable wormholes out of the realm of sci-fi and firmly into theoretical physics. They literally mapped out how an ultra-advanced civilization might pull this off. It involves 3 crazy theoretical steps. First, you'd pull a microscopic wormhole out of the quantum foam of the universe. Second, you'd enlarge it to a classical human-usable size. And third, you'd have to stabilize it so it doesn't just instantly collapse on itself. But, and there is always a massive but in astrophysics. Here's the catch. We have never actually found a traversable wormhole. The biggest problem? Natural wormholes are dismayingly unstable. We're talking so unstable that they would pinch close in a fraction of a millisecond, crushing anything inside. So how do you keep this cosmic tunnel propped open? Theoretical physics suggests you'd need something called exotic matter. This isn't just normal matter. This is matter that possesses a negative energy density or an outward negative pressure. Basically, it creates a repulsive gravity to push outward and keep the wormhole from collapsing. Without it, sending a spacecraft through would be a total suicide mission. And the math gets even more complicated. The physical structure or topology of the wormhole dictates exactly how much of this exotic negative energy you need. If you start adding more tunnels or throats to your theoretical wormhole, the energy cost skyrockets. So just having a wormhole exist isn't nearly enough. The energy bill to keep it open is literally out of this world. So where does that leave us? Well, right now, we have absolutely no practical space travel technology to pull this off. We don't know how to build a wormhole, we don't know how to stabilize one, and we definitely don't have exotic matter lying around. Using today's tech, there is just no practical way to cross the galaxy. But hey, let's not lose hope entirely. Look at human history. We've achieved things that once seemed completely impossible. We've built massive telescopes that let us peer deep into the universe. And when we look out, we're actually looking back in time. Light takes 1 second to reach us from the moon, 8 minutes from the sun, and a staggering 2.5 million years to reach us from the Andromeda Galaxy. We are literally seeing objects as they were millions or billions of years ago. Think about this. If there is an advanced alien civilization sitting in the Andromeda Galaxy right now, looking at Earth through a super telescope, they aren't seeing us. The light they are catching left Earth 2.5 million years ago. They're watching our early human ancestors banging stone tools together.
It perfectly captures this idea: space is not just a gap in distance, it is a gap in time. Just because we can see a distant galaxy doesn't mean we can easily just go there. You aren't just traveling through space, you're battling the flow of time itself.
And that might be the most fascinating takeaway from all of this. Maybe the future of human exploration won't rely on just building faster rocket ships. To truly escape our cosmic neighborhood, we might need to figure out how to manipulate distance itself. If we ever unlock the secrets of space-time, everything changes. So the next time you look up at the night sky and see the Milky Band of our galaxy, remember this: we are just barely starting to explore our cosmic neighborhood. The ultimate question isn't really when will we leave the galaxy, it's will humanity ever learn to change the very distance of space itself? And honestly, the discoveries of the next few centuries might just give us the answer.